Assalamu alaikum wa rahmatullahi wa barakatuh. This is the 7th part of Chapter 11, Work and Energy. At the end of this video, we're going to be able to calculate the gravitational potential energy for some different situations. It's good to remember that we have taken two forms of energies, the kinetic energy and the gravitational potential energy. The kinetic energy depends on motion, while gravitational potential energy depends on the interaction between the body and Earth. The kinetic depends on speed and mass, while the other one depends on weight and the position from the reference. The first one, the kinetic, is positive all the time, while the gravitational potential energy, its sign depends on the position from the reference. Finally, the kinetic energy is half mv squared, while the gravitational potential energy is plus or minus mgh. In the last video, we made an application about the gravitational potential energy, but we were considering the system as a particle with no dimensions. In this video, mainly, we're going to study the two new situations, the case of a pendulum and the case of a ruler. Let's start with the case of the simple pendulum. Consider a pendulum formed of an object S of center of mass G and mass m, attached to one end of a light cord of length L. The other end of the cord is attached to a fixed point O. When hanging straight down, the simple pendulum is in stable equilibrium. Since the mass of the pendulum is considered in the center of S, so we consider our study of the pendulum as the study of the point G that represents the center of mass of the pendulum. To study the gravitational potential energy of this pendulum in its different positions, we are going to shift it from its equilibrium position by an angle alpha, where G becomes at point G1, and then it is released from rest. Take the horizontal plane containing G2 as a reference level for the gravitational potential energy. At equilibrium, G is at point G2, thus GPE2 is 0. The indication of the plane containing the reference level for the gravitational potential energy is important in finding GPE since it depends on the height from the reference level. The question now is calculate the gravitational potential energy of the system pendulum Earth at positions G1 and G2. GPE at 1 equals to mgh1. Let's indicate the height on the figure. The height is taken with respect to the reference, thus we drop the segment h1 and try to find it. We draw a horizontal line perpendicular to OG2. This horizontal line cuts the vertical segment OG2 into two parts. The length L becomes capitalized H plus H1. The length L is given. Then, can I find H, which is OP on the figure? Yes. We have now a right angle triangle OG1P. We can use cosine alpha since cosine alpha equals to the adjacent over the hypotenuse, which is H over L. And H then equals to L cosine alpha. Let's replace it in the equation of L. Thus, H1, which is L minus capitalized H, becomes H1 equals to L minus L cosine alpha. Taking L common, it is L into 1 minus cosine alpha. Let's replace this in the expression of the gravitational potential energy, and it becomes mgl into 1 minus cosine alpha. It is positive since G1 is above the reference. Finally, GPE2 is 0 since the center of mass of the pendulum is on the gravitational potential energy reference and the height is 0. What if the gravitational potential energy reference is passing through O? How would this answer vary? First, the height is now taken between the position of G1 and the plane passing through O. Then, this height is found directly using the right angle OPG1 such that cosine alpha is h1 over L, and finally h1 is L cosine alpha. What about the sign of the gravitational potential energy in this case? It is negative since it is below the reference. Thus, it is written as GPE1 equals to minus mgh1, which is minus mgl cosine alpha. What about GPE at 2? Will it vary? Yes, it is negative mgh2, where h2 is the height g2, and thus it is minus mgl. If you want my advice, it would be better when you practice solving it by yourself. The second case is the case of a ruler or any similar shape like a stick, a ladder, or even a rod. A uniform thin ruler of mass m and length AB equals to L stands at an angle alpha with the ground. Take the ground as a reference level for the gravitational potential energy. Before we proceed, what is meant by a uniform object? A uniform object has a uniform density. Its center of mass coincides with its geometrical center. This means that the center of mass of this object is at its midpoint. To solve such problem, we deal with the given system as if we have one mass placed at point G, which is the center of mass. Now the question is, calculate the gravitational potential energy of the system, ruler, Earth, at position G. First, we identify the height and the position of G with respect to the reference, which is h on the figure. Since it is above the reference, then the gravitational potential energy is plus mgh. H then is found when we consider this part of the figure only, since it gives us the information that we need. In this triangle APG, we can take sine alpha as opposite over the hypotenuse. So it's h over L over 2. Why L over 2? Since we said that G is the midpoint of AB. Now h is L over 2 sine alpha. Finally, the gravitational potential energy at the point G is plus mg L over 2 sine alpha. The last idea in this video, the relation between the gravitational potential energy and the work done by weight. To establish this relation, we're going to consider this situation. A skier of mass m is at the top of a slope, as shown in the figure. Calculate the variation of GPE of the system, skier Earth, between the positions A and B. GPE at A is plus mgha, it is above the reference. Then GPE at B is plus mghb. The variation then is delta GPE from A to B is GPE final, which is B, minus GPE initial, which is A. Writing their expressions becomes mghb minus mgha. Take mg common, it becomes mg into hb minus ha. Do this expression remind you with any expression that we have taken before? Actually, yes. It is the negative of the work done by the weight, where it was given as mgh initial minus h final. Thus, we get delta GPE from A to B is minus the work done by weight from A to B. This is enough for this video. Just remember that gravitational potential energy is due to the interaction between body and Earth, and the gravitational potential energy for a uniform object is calculated for the center of mass, which coincides with its geometrical center. Finally, delta GPE from A to B equals to the minus of the work done by weight from A to B. This is the end of video 7. Thank you for watching.